In this project, we will build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbine speed and heat and recovery stream generators. So what we have here is we have a set of 9,568 hourly average ambient environmental readings from the sensor, and the aim is to be able to perform some basic steps to model, process, and to train and evaluate a machine learning model on the dataset. So that's the objective of this lab. So we have key variables. We have temperature, which is designated with T, ambient pressure, which is AP, relative humidity, which is RH, exhaust vacuum, which is V, and net hourly electrical energy output, which is PE. So what I did first is I did the training data. So I took like 75% for training, which is 7,176, validation 10%, which is 956, and 15% at test, which comes to 1,435, for a total of 9,568. So then I carried out a regression, so a simple regression on the total training data over here. So as you can see, the output, I got the R squared, which is 0.928. So it comes to about 93%. So this indicates that the model is 93% fit, and then the data fits well as well out of all the observations. Then we also have a scatter plot over here, which I've created. So the scatter plot tells you like the distribution of the linear regression and any of the outliers, and it helps you also know about the clustering and the way the variables interact. So from there, I then carried out another sort of regression, but this time I removed a variable. So in this case, I removed humidity, and then I calculated the regression using the data analysis tools in Excel. So here you can see that the R squared is 0.91, which is a bit down from 93%, but it's still quite valid. So together with that, we also get like the predicted PE and then the residual values for each of these. And then the test data, which you can see over here, which consists of 1,434. You can see that they did the calculations over here as well to see the distribution. And you can see the R is around 92.8, which is quite close to 93 as well, together with the residual outputs as well. So then when I compare these two, you can see that the multiple regressions is 0.96, and that they're quite close. The adjusted R and the R squares are pretty close, so it shows that there's a pretty close correlation between the two. Then we'll use these coefficients over here in order to calculate the next section, which is the validation set. So in the validation set, we calculated like the prediction for the P1 and then the errors, as well as the error squared and the absolute error. So what data we ended up getting is that once we did all these calculations, you can see that the mean standard error is 33.4 and 33.35, which is quite close. It shows there is a kind of like correlation between them. And then going down, the percentage of mean absolute error is also quite close, like 29 and 32. So coming back to the lab questions, question number 1, I'd say the type of machine learning model that I felt would be best are the regression models, as there is the modeling of the numeric continuous data. That's why I used regression. Then there's the other modeling type of regression, which I used to calculate the mean absolute square percentage and the values in order to test the credibility of the validation dataset. I removed the column of humidity, similar to a feature ablation test, just to see if there will be any discrepancies in the data. For question number 2, the features used in the model were scatter plots derived from the data variables as the full data set, as I had shown you earlier. and it shows the regression and the outliers and the various type of data distributions which help to better correlate the data. In point 3, I divided the 9,568 records into 3 parts. First, 7,176 for training, 956 for validation, and 1,435 for testing. This way the model gets enough data to learn from some data as well as enough to tune itself, and also a separate set to see how well it performs on new information. I also decided to carry out a normal regression because of the limitation of Excel. I'm also used to AutoML, which segregates the data and analyzes it instantly and then outputs all the information for you. And question number 4, the 2 algorithms and approaches I utilized are normal linear regression because of the numeric nature of the data set, and the second one I used was regression similar to the feature ablation to see if removing it would have a significant impact on the mean absolute error, and if there were any outliers in the data set once validated and compared. I felt that the linear regression on the whole model in the dataset turned out to be the most accurate. And question number 5, I evaluated the 2 predicted models using the validation dataset on 956 records. Both models achieved similar mean standard error values around 33.4, indicating there were comparable averages and the predictions and deviations were comparable. Also, prediction 1 performed better overall with a lower mean square error of about 1,118 compared to 1,736. For prediction 2, the suggested prediction 1 had fewer larger errors. Prediction 1 also had a lower mean absolute error of approximately 29.46 versus 32.94 for prediction 2, showing it's more accurate on average. The percentage mean absolute error was also better suited for prediction. So it's 29.46% compared to prediction 2, which is 32.94%, meaning its errors were smaller in relation to the actual values perceived. So overall, the predictions, I would say, in prediction 1 demonstrates better accuracy and consistency, making the preferred model for this task more viable. So that concludes our lab, where you can see the correlations between different types of regressions. One where you do the whole data set when you remove a variable, in our case was humidity, and then you go and test with the validation data set and see what correlates better.